I will now talk about the parametric cost vector. Parametric cost vector. So, I told you that this is nothing but the dual of the parametric right hand side problem, but we will handle it independently. So, the problem would be minimize z lambda equal to c plus lambda c star transpose x subject to a x equal to b, x greater than or equal to 0. And there can be many economic situations which would probably model into this kind of thing, because sometimes the price vector is also controlled by, is under control by the government, and they might announce different policies from time to time. So, you may want to keep this parameterized through some C star, which probably is known or has been told, and then you want to be able to make sure that the moment the policy is announced, you have access to an optimal solution, right. Okay. So, let us first begin by saying that suppose, so let B be an optimal basis for some value of mu equal to mu naught. So, suppose for some fixed value of mu naught, and most often mu naught is chosen to be 0, and then you obtain an optimal basis by so many different methods that you have learned so far. So, B is an optimal basis for some value of this. So, then it is also feasible, it is optimal for mu equal to mu naught, and you want to now say that, so therefore, the relative cost here, relative cost is equal, relative cost for example for zj lambda minus, okay, I am doing it the other way. See, we are using the notation, some textbooks use it as z lambda minus c lambda, but we do it. So, c minus c is j minus zj, and this as a function of lambda. So, this would be in our case c j plus lambda c j star bar, right, which we write as c j minus z j plus lambda c j star minus z j star, right, because here the z j star is computed with respect to the c b star, and this is computed with respect to c b. C b b inverse a j, and this will be c b bar, c b star, b inverse is the same. So, this will be computed with c b star b inverse into a j. So, this is the thing, right, right. So, then you want this to be greater than or equal to 0. Why am I writing lambda? It should be, I am using the parameter mu here just to distinguish from the right hand side case. So, mu equal to mu naught. So, this will be then mu, okay, mu, and so here also this will be mu, right. So, in fact, right now we are having this as a mu naught, and this is mu naught, because for some fixed value of mu naught, this optimality criteria is satisfied, okay. And now let us define. So, let the same way we will define an upper value for mu naught and a lower value. So, the same basis, since it is feasible, let us say for what values of mu other than mu naught, the optimality criteria will be satisfied. And so, we say that if c j star minus z j star is greater than 0, then this implies that your mu naught is greater than or equal to minus c j minus z j upon c j star minus z j star, right, with c j star minus z j star greater than 0. So, in that case we can immediately, that means if I take mu to be lower, this, let me again define it as mu greater than, so this lower bar with respect to B, I take the value as maximum of all such for which Cj star minus Zj star is positive, max of minus Cj minus Zj upon Cj star minus Zj star, such that Cj star minus Zj star is positive. Okay, so I define mu bar because as long as this thing is positive, for all values of mu greater than mu b bar, this number is the inequality, the optimality criteria would be satisfied. Similarly, you will define your mu upper bar as minimum of minus Cj minus Zj upon Cj star minus Zj star, and your Cj star minus Zj star is less than 0 in this case. So accordingly, and so therefore, we will now define, now see, the thing is that you expect that mu lower bar is less than or equal to mu upper bar, right. If that does not happen, that means the basis is not optimal. It will never be optimal because the interval is empty for the basis B. But here we have started with B as an optimal basis for mu equal to mu naught. So in our case, this is true, and in fact mu naught is a element of this interval which we call as the characteristic interval. So if this happens, then we say that mu b lower bar, mu b upper bar is the characteristic interval with respect to the basis B. Okay. This is the characteristic interval, and as we saw, it can be empty, but in that case there would be no optimal basis B. So therefore, if I just want to consider for some basis a characteristic interval, it is possible that the characteristic interval for any basis need not be non-empty, right. So that is one thing, and secondly, so this is the interval. So now we are saying that this may be empty, right. This is maybe empty, or it may contain, it may contain a single point which means that lower bar is equal to the upper bar, right. It may contain, that means this will be upper bar, right. Otherwise it is a proper interval that has more than one number, and so B is optimal for all values of mu in this interval, right. Okay. Now yes, so what else can we say about it? Yes, you see that the moment you choose a value of mu outside this interval, consider the case mu greater than mu upper bar B, then what will happen, that this number for whichever j this minima occurs, for that index the corresponding relative cost value will become negative. Yes, the moment you choose a value of mu bigger than mu upper bar B or mu less than mu lower bar B, then the corresponding this thing here for whichever the maxima occurs, so that index, for that index the relative cost price will become negative, and similarly here for mu greater than mu upper bar B, the corresponding relative price for that particular variable will become negative. So you will lose optimality for basis B, right. For values of mu outside this, B is no longer an optimal basis, and therefore here the proof is very simple, that the basis, a particular basis will never be repeated, because see, it will not be optimal for values of mu outside this, and so as you proceed with the higher or lower and lower values of mu, that means the moment you leave this interval, optimality of B is gone, right. And so B will never come back, because you are not going to come back to a value of mu again, yeah, you are going to change the values of mu. So therefore here it is very simple to say that the algorithm will be finite in number, right. I mean the number of iterations for the algorithm will be finite in number, right. And also the same argument you can just discuss and show that the overlapping intervals will not be there. The characteristic intervals will not overlap. Why? So now it may contain a single point, or otherwise it is a proper interval. So fine. So once you have this, then you may want to proceed. So for example, if you want to take mu greater than or b upper bar, if you want to do this, so then in that case, of course, if this is finite, yeah, you can see from here also that yes, I should have written this. It's not complete yet, because if Cj star minus Zj star, if there's one single j for which, at least one j for which this is positive, then you can compute this. But then otherwise it will be what? Mu b lower bar will be minus infinity if all Cj star minus Zj star are less than or equal to 0. Yes, you can see from here, from this inequality, if all these are less than or equal to 0, hold on, yes, then mu can be made as small as you wish and the inequality will continue to be satisfied. This is negative for all j, then you can choose your mu to be as small as you want, and the value will continue, this relative cost will continue to be less than 0, right. So in other words, the mu can take values up to minus infinity if Cj star minus Zj stars are all negative. Similarly here, this will be plus infinity, the upper this, if Cj star minus Zj star are greater than 0, greater than or equal to 0, because then it's only the yes, because I can make this very large. No matter what the sign of Cj minus Zj is, if I take mu large enough, then this inequality will be satisfied, provided this is all greater than or equal to 0. So if all these are non-negative, then I can choose mu to be very large, and irrespective of the sign of Cj minus Zj, this inequality will continue to be satisfied. So that means in that case the value of mu will go up to plus infinity if this condition holds, right. So this is important. So therefore here we are saying that you want to proceed with a value of mu greater than mu upper bar b, provided this number is finite. If it's infinite, we don't go beyond that, then I will look at the values of mu less than mu lower bar b, right. So if this is this, then you choose. So what will happen in this case? This is the thing, yes. So suppose minus Cs minus Zs, I hope you can, let me write it carefully, Cs minus Zs divided by Cs star minus Zs star is equal to mu upper bar b. That means this minima occurs for the index s, for the variable s, right. Okay. So what are the things possible? I'll have to come back here. So you find out this thing and you can immediately see that your relative price, so for mu greater than mu upper bar b, your Cs minus Zs mu, right, this relative price is less than 0. So as soon as mu is greater than mu upper bar b, this number will become less than 0. So it will be a candidate for coming into the basis. You want to improve the value of the objective function, right. So what are the two things possible? So you start with a simplex algorithm, look for an optimal basis, because this one is going to enter into the variable xs is going to become a basic variable, right. So then either, yeah, so in that case, see, you may encounter, so as you proceed with the simplex algorithm, you may encounter degeneracy, unboundedness. You may encounter unboundedness, yes, because feasibility is not a problem, since you will, in the simplex algorithm, you will go from one basic feasible solution to another, right. So, once you enter x, you try to enter xs into or you try to make xs a basic variable, then you may encounter unboundedness, right, which means that because this thing is anyway less than 0, which means that is your ys is less than or equal to 0. Your ys is less than or equal to 0. So, in that case, what will you conclude immediately? Because for mu greater than mu upper bar b, this is less than 0, and it will continue to be less than 0 for all mu greater than mu upper bar b, and if the corresponding column underneath is less than or equal to 0, this implies that for this interval, sorry, this will be open, because for upper bar b you have b as an optimal solution. So, this implies that this is the open interval for which the problem is unbounded, for which the original problem for which the original problem is unbounded. Okay. And if you do not encounter the unboundedness criteria, you will get a new basis by including AS into your basic set of columns. You will get a new basis, and again you will find out. So, you may encounter, if a finite optimum. So, maybe I can write this as 2 steps here. These are the 2 possible outcomes. So, if a finite optima is attained, denote the new basis by b bar. And remember, I have not used the word adjacent very often, but when describing the simplest algorithm, of course, we define adjacency and so on. So, anyway, here see b bar and b differ by 1 column, right. You have replaced, you have entered this thing, the AS column here, you have entered AS into the basis b bar, and some column from b, which by the minimum ratio rule you will find out will be taken out of the basis, and AS will come into the basis. So, this is your new basis, right, and then accordingly, so then compute this, and right, I am putting it close, provides the, with the assumption that this is finite. If it is not, then you will have a I mean, you know how to. So, you compute this and proceed. Right. Now, I have already told you why, so, but anyway you write it down. So, show that, so this is a question, show that mu upper bar b is equal to mu lower bar b bar. Okay. That means the intervals, the characteristic intervals that you obtain will not be overlapping, and also we already showed you that the number of intervals will be finite, because the number of bases is finite, since a basis will not be repeated for since you are changing the values of mu at each iteration. So, the number of intervals is finite, and there will be open intervals on 2 ends of the. So, when you are partitioning the real line, so there will be some closed intervals and some open intervals. So, the open intervals will always figure at the 2 ends of the real line, right. Okay. So, that shows you how to continue with this. Now, of course, the question is, so we still have to answer the question as to how to begin with the how to get a starting. See, this was all done with the assumption that b, you already have a b for some fixed value of mu, which is an optimal basis, and then I know how to proceed. So, the one more aspect of this algorithm that needs to be fixed is how do you start with it, how do you begin the algorithm, right, basically. So, let us do that. Yes. This is to point out that instead of writing the interval as mu b bar infinity, I wrote the interval as infinity mu b bar. So, please, while going through the lecture, kindly replace infinity comma mu b bar by the interval mu b bar comma infinity. Thank you. Okay, so how to obtain? Now the question is, how to obtain a starting feasible solution. So, how do you obtain a starting feasible solution? Fix a value of mu, and normally you, for convenience sake, you choose mu to be 0 unless you have reasons to choose some other value, it depends. So, fix a value of mu and you begin with the simplex algorithm. Or one of its variants, or now you know enough of one of its variants, right. It may be that the situation is tailor made for the dual simplex algorithm, or you can give the primal dual, whichever is convenient, or one of its variants. Yeah. So, variants. Okay. So, once mu is 0, it is a regular linear programming problem. You start with use one of the methods to obtain a starting feasible solution and continue, right. So, you may encounter what are the three things that, so 3 possible outcomes are there, right. Three possible outcomes. So, one is the problem is infeasible. Okay. Now, remember, mu is I fixed mu, and then I see that the problem is infeasible. So, it is infeasible because value of mu has no role to play in the feasibility of the problem, right. So, once I, for some value of mu, I encounter infeasibility, then the problem is infeasible for all mu, right. The problem is infeasible. This implies a problem is infeasible for all mu. Yeah, because you are trying to find a feasible solution for A x equal to B x non-negative. So, that has nothing to do with the value of mu. So, for any value of mu, it turns out that the problem is infeasible. It is going to be infeasible for all mu. Right. Second, you find a basis B for which the optimal value is finite. Right. Then you already know, I have spelled out in detail that once you have an optimal basis for some value of mu, then you know how to proceed, right. So, is finite, then proceed as detailed above. As detailed, I have given you the details above. Okay. And the third thing is, of course, you encounter. So, the third would be degeneracy is encountered. Okay, not written correctly. I will rewrite, is encountered. Is encountered. So, you come across the degeneracy, not degeneracy, unboundedness. Unboundedness unboundedness is encountered. Now here the value of mu is important, because for one particular value of mu, because unboundedness depends on your objective function value, and so for some mu it is unbounded, then we have to discover for what other values of mu is it unbounded. So what will happen? Yeah, so here unboundedness is encountered, then so you want to look at the this thing. So that means, yes, so which means this implies that for some t, your Cj minus Zj bar plus mu naught, well, okay, let me call it mu 1, whatever the starting value, mu 1 Cj, I should say t here, this is t, this is t, so this is also t star minus Zt star. This is the thing. Why am I putting bars here? It's not important, because once am I writing, see, either you write Ct bar, which implies Ct minus Zt. So let me not write the bar here, right? So this is less than 0. Yes, this is less than 0, and your Yt is less than or equal to 0. That means as you're continuing with the simplex algorithm, or with whatever algorithm, you come across a column for which the relative price is, current relative price is less than 0, and the column underneath is less than or equal to 0. So you cannot proceed with the simplex algorithm, and you say that the problem is unbounded, right? So now just see, if Ct star minus Zt star is 0, if this is 0, what does it mean? It means that Ct minus Zt is less than 0, and your Yt is less than or equal to 0. So once Ct star minus Zt star is 0, the relative price becomes independent of t. So therefore, what would you conclude? This implies that problem is unbounded for all mu. Okay, because the moment Ct star minus Zt star is 0, the role of mu is out. Okay, and this will continue to be satisfied, the unboundedness criteria. Okay, then you can have Ct star minus Zt star greater than 0. If Ct star minus Zt star is greater than 0, then you can define mu t as minus Ct minus Zt upon Ct star minus Zt star. Yes, and what do you see here? Ct star minus Zt star is positive. So then, if I choose my mu to be, see, remember, you want to see for what values of mu will this continue to be, will not be satisfied, because I want to know, well, will I be able to get out of the unboundedness condition, right? So you want this to be, so okay, you look at here, this is thing, and you want this to be, so this would be, that means Ct minus Zt. Yes, I do it, and I bring it here, plus mu t Ct star minus Zt star. I want this to be positive. So right now it is 0. So that means I take value of mu, which is such that this is positive, right? So which implies what? Which implies that your mu should be greater than, because this is positive, should be greater than or equal to, then equal, so is minus of Ct minus Zt upon Ct star minus Zt star, because this is positive, right? So that means for mu, so this implies that for mu greater than or equal to mu 2, the optimality criteria, the degeneracy criteria will not be satisfied. For mu less than mu 2, the degeneracy criteria will be satisfied. So that means I can then proceed. So in case Ct star minus Zt star is positive, then I can start with values of mu bigger than mu2. Mu2 is this number, right. So, I will start with the value of mu bigger than mu2, and in that case this particular relative price will become positive, and so the this thing will be yeah. So, therefore, this will no longer be a problem case, because this has become positive, and so y t less than or equal to 0 is no problem, right, and I will continue with the simplex algorithm. So, this is it, right, and of course, similarly you can argue for C t star minus Z t star less than 0. In that case, your mu2 again will be this number, but then for mu less than mu2 you can proceed with the simplex algorithm. So, for mu greater than mu2, the problem would be so depending on the sign of this number, which you would know when you are solving the problem. So, if this number is less than 0, then you will say that for all mu greater than mu2, this number, the problem is unbounded, but less than that mu2 number, the problem may not be unbounded. You do not know, but you can at least proceed with the simplex algorithm, because then this number is this is no longer less than 0. I mean, your unboundedness criteria is gone, right. So, now you again compute with a begin with a simplex algorithm, and depending on, it is possible that you may again encounter unboundedness. So, there will be another value of mu2, I mean there will be another value of mu, we can call it mu3, and so you will continue, but after a while you will get out of the unboundedness, or the unboundedness may continue, but anyway. So, we know the method, right. So, for some t this is this, and so what we are saying is that if this is 0, problem is unbounded for all mu, and if this is positive, then you have a mu2, and for mu greater than mu2 you will not have let me not write this, right, because mu has to be strictly bigger than mu2, and similarly we can write it out for. So, let me record it so that one wants to read it and look at it, and similarly for C t star minus Z t star less than 0, you want that for yes. So, what did we say for mu? Mu less than your mu2, which is minus of C t minus Z t upon C t star minus Z t star. Yes, the algorithm may be continued. Okay. So, you continue with the algorithm, and so in any case all the stumbling blocks are over, you know how to handle each situation, right. So, let us now look at an example, and then if something is left out here, hopefully we can cover it in that case. So, the problem is stated here. This is your C, and this is your C star, okay. And so that means this corresponds to minus Z, and this corresponds to minus Z star. And then right now this is the tableau, so it shows you, see, immediately you see that x1, x2, x3 is a feasible solution, because the right hand side. So, in this case we do not have the problem of having to first find out a starting feasible solution. I had done it in the parametric right hand side case. So, I thought in this case I will just begin with the simpler problem. So, here x1, x2, x3 is a starting basis. Since the prices are all 0 here, CB and CB star, therefore, the Cj minus Zj's are also the relative prices, that means Cj minus Zj's, because Zj and Zj star are all zeros here, right. So, this is the thing, right. Now, I thought this problem I will solve by using the inverse Tableau technique. So, let us see, this represents your starting basis. So, the basic values are right now 1, 3 and 7, objective function values are zeros, and your basis is x1, x2, x3, and the inverse Tableau is all identity, because this is identity and this is this, right. So, this is the starting thing. Okay. Then you can check here, okay, is optimality satisfied? no. So, we therefore, yeah, we compute the right. So, these are the actually these are, as I said, these are the relative prices, right. So, from here you see that for the positive one you will compute what will you compute. So, I have written them that is for the other one. So, that is the second tableau. We will do it right here. See here the ratio would be 6 for positive 1, which will give you the lower value of mu, and here this is minus 12 upon 2, which will be minus 12 upon minus 2, which is 6. So, that means your, in this case, your mu b lower bar is mu b upper bar, which is equal to 6. So, this is a singleton case. I hope this is clear, because you see these are your relative prices with respect to C and C bar, C star, since your matrix is identity matrix, that basis matrix, and these are zeros. So, your CBB inverse is 0. So, simply Cj minus Zj's are simply Cj's. So, therefore, for the positive one, there is one positive one. So, here this is 6 upon 1, which is 6. So, the lower value is 6, because only one positive, and for negative ones you have minus 12 upon minus 2, which will be 6, and minus 30 upon 3 would be 10. So, the lower number, remember, for the upper this thing you need the minima. So, the minima would be 6. So, therefore, this is a singleton. So, that means your basis, what we are saying here is that x1, x2, x3 is the basic variable, basic solution, is the basic solution, basic feasible solution, you can say, basic feasible solution, right, and it is optimal for lambda equal to 6. So, I did not have to do any extra effort to compute the starting basis. I got it by inspection from here only. I could get an interval which, see, if this interval is empty, that means if this value was bigger than this value 6, then this interval would have been empty, a vacuous interval, and then I would have concluded that B cannot be an optimal basis for any value of mu. But we were lucky, we got one value of mu, for which again I am writing lambda, because this is mu is equal to 6. Okay. So, this is the optimal solution, and therefore, when you have to now a choice of considering mu greater than 6 or mu less than 6. So, suppose we continue with this one. If I do this, then this number, your C5 minus Z5 with respect to mu, this will become negative. Yes, because if mu is bigger than 6, this will become more than 12. So, 12 minus something negative, which is more than 12, will be negative. So, that means your this x5. So, for mu greater than 6, x5 becomes a basic variable. Okay. So, x5 becomes a basic variable, and we then, this next table will show you how to. So, here x5 becomes a basic variable, and then the idea is that you should be able to x5. Yeah, if you, let me see if I am considering this thing for. So, see here, as I said that in this case, this is the variable. If I am considering, okay, so I am considering mu greater than 6. This is the case we are looking at right now, and in that case, this relative price will become, for x5 will become less than 0. It will be a candidate for coming into the basis. So, here, for lack of, I am doing the calculations on this side, but right now in this case I am writing this, because remember, for the inverse tableau you write out the column, pivoting column here, and then you do the pivoting. So, this column again, because my B inverse is identity, this column comes here as it is. So, this is 12 minus 2, 1, 1 and 2, right. And for the pivoting thing, I have to take the ratios 1 upon 1, 3 upon 1 and 7 upon 2. So, this is the smallest ratio. So, let us quickly pivot on this one. I have already done the calculations, which means that nothing changes here, because this is 1. Then you subtract this row from here, right, which is shown here. Oh, it should be 2. Yeah, sorry, because you are subtracting this from here. So, this will become 2. I am sorry, this is 2. Okay, fine. and then you are subtracting twice this from here, right. So, twice this from here, so that should be 5, this is okay. So, this one is 5, and then you want to multiply this by 12 and subtract. So, this row you multiply by 12 and subtract. So, what will it become? Yes, it shows here, right, because this will not change, it is only 12 here. So, you minus 12, that becomes minus 12, and the objective function value will also, this is 1 here, you are multiplying by 12 and subtracting. So, your minus z is minus 12, right, and then you want to multiply this by 2 and add. So, when you multiply by 2, this becomes 2, right, and this will become 2, and this is 0. So, and then of course, and we have done the pivoting here. So, this is your new tableau. This is your new tableau, okay, the inverse tableau. And now again we want to check, look at the, so remember the only thing that in this case you have to do is you have to compute these rows of C bar and C bar star, because in the inverse tableau, so I need to know the ratios, right. So, that is not difficult, because see, you know that this is your CB minus CBB inverse is minus 1200, right, and your minus CB star B inverse is 200, right. So, you need to compute, say for example, C1 minus Z1 mu, I am saying here, right, whatever the notation. So, this would be simply your C1. So, the original this thing I have with me, that is 0. So, that is 0. So, I simply need minus Z1, yes, minus Z1 whatever the value of mu. So, minus Z1 would be what, and so this is equal to minus Z1 minus mu Z1 star, this is what you have, right. So, so what is minus Z1? Minus Z1 is simply minus of CB star B inverse. So, I have just this and multiplied by the column for the A1. So, this is only first entry here. So, the first entry is so minus 12. So, this is minus 12. Similarly, the first entry of star thing is here, right. Then 2 and 3 are basic variables. So, this is 0, and for x4, what is your column? Your x4, the column is minus 1, 0, minus 3, yes. So, you need to, let me just again show you the calculation. So, if you want to compute, yeah. So, okay, let me write C4 minus Z4 only. So, C4 minus Z4, C4 is minus 6. So, this is minus 6, and then this is minus, so this which becomes this, which is plus minus 12, 0, 0 times the column which is minus 1, 0, minus 3. So, okay, minus 1, 0, minus 3. So, that becomes plus 12. So, this becomes 6. So, plus 12 minus 6, that becomes 6, right. And similarly, you can compute minus 1, and then you can compute 42 and minus 5, yes. So, now you want to compute the, that means for the new basis consists of the basic variables x5, x2 and x3, yes. For this set of basic variables, now you compute the lower and upper limits for the mu, such that this basic feasible solution is optimal. So, here for the positive one, the ratio would be 6, yes, I am writing here. Then for the negative ones, this is 6 and 42 by 5. So, here again the new basis is optimal, because this is a smaller minimum and this is a maximum, there is only one entry here. So, therefore, what we have concluded is that the new basis is again optimal for a single value of mu, right. So, that is the conclusion. So, for mu greater than 6. So, well, okay. So, well, we have that the basis or the basis, shall I say A5, A2, A3 is optimal for, I should have said here this, for mu equal to 6 only. So, that means I still have to then proceed further, right. So, in a way you can say that maybe I would not yeah, okay. So, that is it, fine. So, then but what will you do now, because you have a new basis. So, you have to again check. So, for now again you want to look at mu greater than or equal to 6. So, in that case this will be a candidate for entering the basis, right, x4. So, x4 is to become a basic variable. Okay. X4 is to become a basic variable, and I already have this numbers here. So, what I am showing you is well, okay, why am I choosing 6 minus 1 and not minus 12 2? What is happening for x4? Yeah, because you see here I am choosing yeah, okay, fine, yeah, this is okay. This is your x4. This is your corresponding to x4, this is the thing. So, yeah, just to minimize the space thing, I am doing it this way. 6 minus 1, right, and the corresponding column is for x, I mean the y4. The y4 column we have to write down, it's minus 1 1 and minus 1. Okay. A4 you have to write down. So, because your basis the inverse has changed, this is your new inverse. If you want, we can do the calculation quickly. So, what is your A4? So, Y4. Y4, this is see 1 0 0 minus 1 1 0 minus 2 0 1, and the original column is minus 1 0 minus 1 0 minus 3. So, this comes out to be minus 1, and then this would be plus 2 minus 3. So, this one is 0 because oh, okay, no, this is 1, this is 1, and then this will be 2 and minus 3. So, minus 1. So, this is your y4. So, minus 1 1 minus 1, and these are your relative prices with respect to the C and C star. So, then you want to pivot here, and the pivoting element of course will be just this. Okay. And calculations are not difficult, because what you have to do is simply add this row to this and add this row to this. So, that should be immediately. So, here this becomes 0 0, yeah, and this becomes 1 and 0, this becomes 3, yeah. So, this calculations you have to just correct. So, this is 3, yeah, and this would be 2. So, this will also change because you again adding. So, this becomes 7. Okay. This is 7. So, this becomes 0 1 0, then you add this to this. So, then this will be 0 1 and 3. Why is it sorry, you have to add this to this, you have to add this to this. So, this becomes this is 0 1 1 and 1 0. So, this is what you have, right. Okay. And 6 times you subtract, 6 times this row you subtract from here, and you can verify that this is okay. These are the calculations. Yeah, the only thing is that yes, you are multiplying by 6. So, so this is 2 and you are multiplying by 6 and subtracting. So, 12, how come I have minus 6 here? This is not correct, because you have 6 times you have to subtract. So, minus 24, it will become minus 24, sorry, right. And then you are just adding. So, this will become 4. See, the number that has not changed, it's just that, yeah. Okay, so this is 4. Yeah, so I'm glad that the corrections have been made. So, this is it. And now again in the same way as I showed you, we have to compute the relative prices here, and yeah, either we can do it or we can make use of the calculations I have already done. You need to compute again x1. So your basis consists of x5, x2 and x3. So actually I need to compute them for x1, x4 should become positive and x6. These are the things, right? Okay, because I know that my basis consists of x5, 4 and 3. Okay, this basis I entered x4, so x4 replaced x2. So okay, so this is, that means I don't have to consider this. I have to consider x1, x2, and but that's it. These three I should need to compute. X1, x2 and x6. So quickly let's do it. And so this is your this thing. So what is your C1 minus Z1 bar, this function of mu? Yeah, okay. So what is it? So this would be minus 6. What is your C1? C1 is 0. So this will be simply minus 6 0 times A1, which is 1. So this is minus 6. So this is minus 6. And what is your other vector? The other vector is from here 1 1 0 1 1 0. Remember, this is in the form minus CBB inverse. So I don't need to do anything here. So 1 1 0 and then again 1 1 1 0 0. So that's 1. So this will be 1. Okay. Fine. Then for x2. X2 you are writing minus 6 0, and then x2 column is 0 1 0, so that becomes minus 6, this becomes minus 6, and the other one is 1 1 0, that one is E2, so this will be simply 1. So this is again 1, right. Now for x6 it's minus 6 0 times your this is minus 1 minus 2 and 1, right. So but and C6 so this becomes plus, because C6 minus this thing and you're writing minus this, right. So this is it. So C6 is how much? 30. So this should be 30 plus 6 plus 12. Yes, plus 6 plus 12, and this is 0. So 48. This is 48, and your 1 1 0, the star thing, this would be this. So that would be 30 plus, oh sorry, not 30. What is the price here? That is minus 3. So minus 3 plus this, and again you write minus 1 minus 2 1. So how much is this? Minus 3, then minus 1 and minus 2, minus 3. So minus 6. So this becomes 48 minus 6. So these are, so the ratios here would be 6 6, and this would be 8. Or see, the idea is that you write the upper thing here, 8. So immediately you see that the new basis that you have, which consists of the basic variables x5, x4 and x3. So for this set of basic variables, your interval now is, so that means the characteristic interval is 6 and 8. Okay. So this is the characteristic interval. Before that you had a singleton, this, and below 6 we have yet to consider. So these are the two characteristic intervals that you have obtained, right. And yes, that part I did not complete with you. So right. So therefore now if you want to consider, so for mu greater than or equal to 8, immediately you know that, because this is the only value, right. These are the lower things. So here x6 becomes a candidate for coming into the basis, right. And I have shown the thing here. So we need to compute this for, okay, what I can do is I can simply show you the, so this is out, well, okay, this is your basic feasible solution. So what we need to do is, so I have written out 48 and 6 were the, I wrote out the numbers, and yeah, okay, that's okay. It should have been minus 6, sorry. This should be minus 6, right, because that is the upper limit. So 48 minus 6, and this is your y6. So this is the thing now, and let's quickly, the pivot element would be simply this, because this is the only positive one, and so we pivot on this, we make zeros here, we make zeros here. So the new Tableau, if I want to write down 48 minus 6 minus 2 minus 1, and this is 2. So let me quickly show you that the inverse Tableau would be, so here, okay. So this is your minus z star, this is this, and so this I am showing you after pivoting. So this table is after the pivoting, okay, and the numbers are 1 0 66 minus 30 minus 24 0 1 minus 8 4 3, okay. This number becomes 198. I'll check, and then we'll correct it in the next lecture if possible, because since I made the correction here, so the calculations have to be carried forward. And your new this thing is x5, x4 and x6, because x2 gets replaced, x3 gets replaced by x6, and the basis inverse, this calculation is okay, are 0 0 0 0 0 0. This is minus 3, minus 5 by 2, and minus 3 by 2. This is 2, 3 by 2, 1 by 2, 0, half, half. This side also will have to be checked, because I have been carrying it 3, it's actually 2. So we'll make this correction. Right now this is, I am writing it as this without this thing. So this is the new Tableau, and you see that here the upper limit is, see this is giving you 8, which is your upper limit here. So the lower limit, because for the positive ones you get the lower limit, that gives you 8, sorry, I mean the maxima. The maxima would be, this would be, the maxima would be this one, because this would be less than 8, right, 4 7s, 7.2, and this is 8. So this is the upper limit, the lower limit for the new basis, and the upper limit now is mu b upper bar is 8.8, 8 8s are 64, so 0.25. So that means your new characteristic interval is 8.25. Okay, and so we continue with this. Of course, this correction also has to be taken care of, and the objective function values may also be they may not change, but since we are pivoting on this element and not on this, so I'll continue with that.